Today we have a pretty short lesson on how to use Desmos to make a regression equation, which is a somewhat fancy word for line of best fit. So what we have on the screen right now is population data from the state of Virginia, and we're going to enter it into the calculator as a table so that way we can graph it and make a line of best fit. I got this table, by the way, using the plus button up here, add item. You can add a table. That's where this came from, and I've already gone ahead and typed in the y values because that was going to take a little while. But I do want you to notice that just to make it go a little bit faster, I typed them in millions. So 691,737 I typed in as 0.69 million. And I rounded a little bit to the nearest 10,000 just to make it a little bit easier. And then for the years, I certainly could type in the years however I want, but Desmos might give me problems using such big x values a little bit later on today. So instead, what I'm going to do is use the year 1800 as the year 0, x equals 0. So that'll be where my y-intercept is. The reason I did that instead of 1790 is only because then the years like 1870 will be x equals 70, and that'll be a little bit easier. So one thing I want to show you then is if you type in Desmos an x value for negative 10, 0, 10, 20, 30, 40, and what I wanted to show you didn't work because I had already typed in my y values. Had I not typed in my y values, Desmos would have figured out my pattern and it would be filling these in all automatically for me. I didn't know that wasn't going to work until just now. Okay, so now that they're in, there are two things I want to tell you about finding the window. The first is that making a window from a scatter plot is easy because you have the numbers right in front of you. So I need my years to go from 1790, which is negative 10, so I'll give myself a little bit of extra room there, negative 20, until 2010. I'm going to go at least through modern, like today's date anyway, so I'm going to go up past 2020, which would be 220 or 230, just to give myself plenty of room. And then the y values, the lowest I get up here is just under 1 million. So you know what, I'll just start it. I like having a little bit of space beneath my x-axis. And my y values, they max out at about 8, which, you know what, it looks fine to me. I could make it a little bit lower. I don't need to go all the way up to 12, but I'll stop there. And there's my curve. I do want to show you something else, by the way. In the corner of the table, there's a zoom fit option. If you click that, Desmos will make a window. It usually is a little bit more zoomed out than I like, so I'll usually zoom in, but it is a nice little shortcut. The next thing we're going to talk about is using a linear regression to model a line of best fit. We can see that the population is clearly going up. You learned in Algebra 1 how to draw a line across your graph called a line of best fit, or regression, a linear regression, to use that to predict the population in any given year. Some of you may remember how to do this on Desmos. It's a little bit odd, but it's pretty much just typing the equation that you want, y equals mx plus b, if we want a linear regression. But the two differences are when we type the y and the x, we need to tell Desmos which y values and x values we're talking about. Since I had used the names, since I had used the name x1 and y1 in my table, those are the names I'm going to use here as well. Difference number 2 is that instead of an equal sign, the way we tell Desmos we're talking about a regression prediction is with the tilde sign, which on your regular keyboard is right next to the 1. You don't need to pull up this keyboard or anything to get it. And then you can type in whatever equation you want. If I want a straight line, m times x plus b, and it gives me a straight line. Down here, it tells me what it calculated m and b to be. So if we can remember those numbers, 0.029 and negative 0.173, that's our equation of a line. Now, if we look at that, we can see it's not a very good equation. It's not a very good prediction. We can look at it, an example for that. So I already forgot the numbers that we used. It was 0.029 and negative 0.173. So if we wanted to estimate the population in 2020, 0.029 is our slope times the year 220 plus negative 0.173. And that's our prediction right there. And we can see that that's not that close. As the population really spiked up in the 1900s, the second half of the 1900s, we can see the linear equation was not a very good prediction. It wasn't a very good prediction here either, or down here for that matter. So what can we do to make our prediction better? Well, we can try and match the shape a little bit better. And some of you might have thought already, well, that shape isn't a straight line. That shape is an exponential curve. It seems to be pretty flat back here and then steeply increases and grows what we recognize as exponentially. So we can try making an exponential function instead. We use Desmos in exactly the same way. We type whatever equation we want into Desmos, and it will, using the variables that we typed into our table, and it will figure out what the parameters in our last equation, that was m and b, the slope and y-intercept. In this equation, it'll be the coefficient and the base, a times b. It'll figure that out for us. So y1 is approximately equal to a times b to the x1. And the hint for you is, for an exponential function, don't bother with horizontal compression or vertical shifts. They're not really necessary. So keep it simple. And here's my graph. Y equals 0.5 times 1.013 to the x. And that's my graph. The reason I type that out is so that I can copy it and paste it on the next slide. So now if we use that for 220, we can see that 8.57 is a much better prediction for what the population will be in 2020 than our original one was.